if you look at the going through audio, you'll see that there was a section where we went a little bit ahead on some of the sensing stuff, and we're going to pick up on converging sensing in the mind after we get through memory. So now we're going to be talking about memory because before you can make sense of things, I didn't mean to use the term there, but before you can make sense of things like your senses, you're going to have to interact somehow with memory to make sense of the things that you saw through your senses. So we're going to spend 2 to 3 days on memory, depending on how fast we get through it. Definitely all this week. Now this quote here, it's a little different. Oops, sorry. Different than the typical quote. It's a little long, but basically, I just thought it was kind of funny. This is a guy named George Nagy. He was born in 1937, and I ran across him as I was looking for some good references to give you on analog memory. It's been a long time since there was a really focus on analog memory. Most of the focus now being on digital memory. But when it comes to implementing artificial systems, and we understand more about how the brain works, I think you'll see that it's going to be important to use both analog and digital types of solutions. So I wanted at least to have you become familiar with what an analog memory is and some types of things that perform analog memory functions. So I'm going to go through some today, but I also found 2 articles by George Nagy, one specific to analog memory and another one that's more of a survey using different types of technologies for neural networks, although back then they called them nerve nets. And just to give you a time frame, this is back in the 1960s. Before even I was born. So he wrote this this review in 1968, which I'm quoting from here. It's not part of your assigned reading, but the reference is there if you're just kind of curious. You can just look at that reference. It's on the internet. I didn't make it part of your assigned readings because it's pretty technical and detail, a lot of math. But if you like technical detail on math, it's a really great history of artificial intelligence that was written in 1968 as a retrospect of basically artificial intelligence work that they've done, say, within the last 20 years of that, so back in the 40s. And you'll see a lot of, if you do pull that up, like I said, it's not in your assigned reading, you'll see a lot of interesting references to the same types of things that you see today regarding training and neural networks and layers and learning and supervised learning. A lot of concepts that we attribute today to artificial intelligence are concepts that were first introduced back in the 40s. So it's a little bit interesting to see it here. So he wrote this: we have accompanied the reader into the labyrinth of pattern recognition, pointed out some of the salient landmarks, and offered battle on their behalf to the minotaur of semantic difficulties. We hope that we have given them enough strength to encourage them to return. I thought this was interesting because this is a journal article that was published in Proceedings of the HPAI in 1968. You'd be hard pressed to find this kind of literature sort of language in technical journals, of late. So, if you want to know what a minotaur is, if you play Magic the Gathering, it's a rendering of a minotaur. Does anybody here play Magic the Gathering? Okay, so this is the required reading I don't expect you to be an expert on the analog memory devices, but I do expect you to familiarize yourself with it enough so that you can at least recognize basic differences between analog memories and digital memories. I think that's important. Each one has their advantages. And so that first article literally goes through a bunch of different types of analog memory devices that were known and had been or were being developed back in that time frame. Certainly in 1962, which really was based on his thesis, which he published in which was then in 1960. And then he was invited to do a review article that's different than the one I mentioned earlier. This one he did in 1991, and it was really more in the form of a letter. So this last one's actually only 2 pages long. It's very readable. I found it enjoyable, and I think you'll find it enjoyable too. Again, because it takes you back here now to 1991, which is 28 years ago. And it talks about neural networks. But here specifically, it talks about, at least mentions a special purpose analog, parallel analog. So I just mentioned a little while ago that we tend to think of things in the digital regime. The world by large is the analog world. And when we solve problems and put in solutions, we need to remember that we can borrow from both technology spaces. Just a reminder that the homework number 4 is due Wednesday night, this Wednesday, and that's the original due date. If you have not opened it up and looked at it yet, which I know some of you have not, I encourage you not to do it the last day. I have gotten already some questions. Just want to make sure people are clear on what the questions are. I did put an example of what an answer could look like on Piazza. I believe that's for question number 1. So if you haven't looked on Piazza, you haven't done question number 1, you might want to look at the example. Okay, so we're going to go through artificial versus human memory. We're going to do this a little bit differently than we did the senses. In the senses, we talked about how senses work in humans and other animals, and then we talked about how artificial senses worked. Right? Here, we're going to flip it. I am going to talk a little bit about human memory, but I'm going to save most of the discussion for human memory for the next couple of classes. So we're actually going to jump into artificial memory, and I'll explain why in a little bit. So after we have a few slides on memory, on human memory, we're going to jump into artificial memory. I'm going to go through digital memory, which should be reviewed for a lot of people. I'm going to go through it at a fairly basic level. And then, but if it's not, let me know. And then I'm going to go through analog memory, which I'm guessing most of you, if you've ever heard of it, aren't familiar with it. So I want to give you a specific example so you can understand what that is and how it works. And then we're going to start on human memory, I hope. Okay, so this is a computer program that you can download for free from the internet. It's called Brain Explorer 2. It's made available by the Allen Institute. Basically, the Allen Institute has a commitment to the brain and understanding how the brain works and making that available, making the information available to the public. This is Allen with Paul Allen. Does anybody know who Paul Allen is? Someone should know who Paul Allen is. History. He's a really important person in the history of modern computer science. I'll give you some hints and then we'll see. He recently passed away, actually. So recently, like within the last couple of months. He was the owner of the Seattle Seahawks. Me and a buddy named Bill started a company in a garage. Anybody know who this is? Is that who is Paul? Yeah, his buddy. So sort of like Wozniak is to Jobs, Paul Allen is to Bill Gates. So he's the co-founder of Microsoft. Unlike Bill Gates, he left fairly early and took his billions of dollars, did things like buy the Seattle Seahawks and started the Brain Institute before he passed away. Relatively young guy. So this is what this allows you to do is basically play with brains. It allows you to play with a few brains that have been extremely well analyzed post-human history. Meaning that these few brains are dead, don't need to science. What they did essentially is freeze the brain very quickly and then slice it into very large numbers of very big slices. And literally pass these out to a bunch of interns to diagram the slices, and then did biochemical analysis of a lot of the slices to figure out what genes were in the slices, what genes were in the slices. So, and then they put this all into what they call a brain atlas. And the brain atlas exists for a few individuals, something like 5 or 6 individuals that had their brains super analyzed. And part of the criteria was after their death, they couldn't have had any brain damage. However, they died. And they had to have a healthy brain, basically. People not known to have any sort of brain issues, and they had to get the brains to them so that they could, I guess, freeze them within like 24 hours because they wanted to preserve the chemical content as much as they could of cells before the cells started to degrade so that they can then analyze that. And if you go through here, you can actually take this brain, I have it in transparent view, and you can rotate the brain, and you can look at the outside of the brain, the inside of the brain, and then you can select here what parts of the brain you want to look at, so you can turn some parts of the brain on. What you're looking for is the content of those areas of the brain after this slice and chemically analyzed. So they would look at a certain slice in a given area, to pixels, if you will, and they would basically say, okay, what genes can we find in the cells that are in this area? And they would find those genes and we would put in then how many of those genes are there, color code it, and so you can, every one of these little areas corresponds to like this very sophisticated biochemical analysis and gene analysis of that very specific segment. Pretty cool. And the idea is by making that available to the world that people will go in there and figure out what it all means. Okay. So some of my observations are that it's fascinating. Certainly a huge project to think about slicing the brain into so many little pieces and so many little areas, and you get so much data from each one, and then preserving that slicing to create basically a three-dimensional atlas. But keeping in mind that this brain is comprised of 80 billion neurons and over 80 billion other cells. The neurons are sort of the Hollywood stars of the brain, but the brain isn't just made up of neurons. There's other cells in the brain that do other things. And so there's over 160 billion cells. They're all dead. Okay, so by the time it gets there, they preserve the chemical composition. But it's not like this, you know, the brain's doing anything. It's basically fixed. It's sort of frozen in at some point in time. So there's not information there about how the brain is changing. It's just fixed in time. Obviously, we have 23 chromosomes made up of a bunch of DNA, somewhere on the order of 25,000 genes, any of which can be expressed within any of these cells. So to me, it's very exciting, but the other time, it's a little discouraging because there's just so much complexity. But on the other hand, it kind of suggests what I already know, which is the brain is in large part what makes us human beings. So if it was overly simplistic, then it could be discouraging because we might think that we're not as cool to think that we are. But it's not. It's very complex. So the fact that we're all sitting here different and we change over time shouldn't be a surprise based on the complexity of what's in the brain. Now we're talking about the brain in these few slides because that's basically what we have to talk about if we want to understand what we're doing. So despite all this progress, despite what I just showed you, despite the sequencing of the human genome, despite all the MRI studies and evidence that are out there, and a lot of animal research that's done mostly on rats and mice, pretty much as a scientific community, we don't know how human memory really works. It doesn't mean we don't know aspects of it. Similar to say, well, we know a car works because there's four wheels and engine, and you put gasoline in it. So that tells you something about how a car works. It doesn't really tell you how it works. Same with the human brain. So we don't know how memories are encoded. We don't know how memories are stored, whether it's just neurons or whether it's neurons working with other cells. We don't know how the other cells participate in memory. And we don't know actually how processing, how we do things, really don't know how to do things, is stored versus facts and data information. So we process memory about how to add two numbers, 83 plus 42. We go through the process to figure that somehow. If they remember how to conduct that process, they remember what the number is that's 83 and 42. So I just spent three slides to share with you that we really don't know how to do. But don't feel discouraged because you might remember from the first class that we all had access to a person that we know really well, which is ourselves. We can at least begin to put together how memory works and what it must and mustn't, at least must do by looking into ourselves and analyzing ourselves. A lot of people have done that. We're actually going to do that together as a class, as opposed to just learning what other people have figured out in some exercise. We're not going to do that yet, though. First, we're going to talk about computer memories. We know how computer memories work. That's why I decided here to start with computer memories first and then go to human memories second. And thankfully, for our class today, computer memories are fairly straightforward, at least when you're talking about digital memories. Digital memories pretty much store stuff and you retrieve stuff from them. And the things that you store, there are some exceptions, but by and large, you're going to store them as ones and zeros, which are by and large voltages or charge quantities in a cell. And that's it. There's nothing else really to it. Whatever data or information, or you have a picture or video game, you have some software program you wrote, You have data that you reported. You have a cell phone call that's coming in, someone's talking to you. You record the call, you do something on WhatsApp. Whatever it is that you do, there's a memory that you're storing. We call it software ones and zeros, which in the electrical world is voltage at one level or voltage at another level, or charge at one level, charge at another. That's it. It's a huge $1 trillion industry over the course of the last 10 or 20 years. But at the end of the day, if you work in the semiconductor industry or other industries closely related to memory, what you spend your time in is figuring out how to get things into a medium that's going to reflect ones and zeros, and out of the medium it's going to reflect ones and zeros. And you want to get stuff in and out as fast as possible. You want to be able to make that as cheap as possible. And that's it. So I'm going to show you some memories now. But so when you store, what you do is you take your data in whatever form it's in, whether it's program or it's a picture, and you're going to encode that in some way to some file format. And that file format is then going to be stored into the medium in ones and zeros. And then when it's time to read that, you're going to access the ones and zeros from that media, and then you're going to decode it so you can use it for something. And the things that you're going to use it for primarily are displaying it in some way on a screen, outputting it to a speaker so you or someone else can hear it, transmitting it to someone else, doing some computation associated with it, and or restoring it. That's it. I don't know if you've ever thought about it, but sometimes it's nice when things are fairly simple. I will tell you here, I will just comment on this. When you display it, ultimately you're taking that data and you're going to convert it into an analog form. Because that's what comes out of the display is light in an analog form that your eye is going to be able to receive and sense, like we talked about in class. Or it's going to come out of a speaker in some analog form. It's going to move some membrane, which is going to move the air, which you remember then it's going to move the drum in the ear, which then you're going to get to hear quickly. Other than that, generally it's kept in some digital form. When it's transmitted, it's kept in a digital form, but ultimately it's enclosed in an analog envelope, if you will, when it goes into the air. There are a few different types of memories in computers. There are long-term memories, which are non-volatile memories, meaning they're non-volatile, they don't go away. So it's something you store on your hard disk or on your solid-state drive. Then there's volatile memory, which is short-term memory, which is what your computer is using when it's actually running the program or showing you something on the display. And then there's a really important, often overlooked memory in most computers today, or cell phones, which is what I call immediate memory. This is memory that's actually right there closely coupled to the CPU, to the central processing unit. And it's actually normally now on the chip, on the same chip that's doing the crunching. I'm going to talk about that memory in its own slide a little bit now. And remember, the memory, in a way that's kind of similar to what I described for humans, is for instructions and data. Instructions being how something is done, and data being the thing that you do the instructions with or to. Sometimes, obviously, data can be an instruction, so you can do instructions on instructions. I'm going to zoom this up here. And just as a reference, because I don't know what you take with respect two computing devices before you come to this class. Has anybody not heard of like a DRAM? Let me put it differently. Who has heard of a DRAM? It's okay if you have. Okay, so this is good, and I'll go through this in a little bit more detail. So in your computer, I told you basically have three different types of memory. You have long-term memory, you have short-term memory, and then you have what I call immediate memory or cache memory. It's on chip. So we'll start with the long-term memory first. Long-term memory can be in a lot of different media. It's a long-term memory. I don't know when this was last used. You put this in somewhere, you're probably going to be able to read this. It's not on here. It's floppy. You have flash drives, like little thumb drives. You have CD-ROM, you still have some music that's on CD. SSD is solid state drive, that's what's in your phone. And in some computers, my Mac has a solid state drive. Most laptops I think today have solid state drives. If you have a hard disk drive, you actually have a spinning motor in your drive. So a lot of times you'll hear it start spinning. And you may have a fan. That's different than these other, well, no, hard disk drives, compact disk, somewhat similar. Solid state drive and USB flash are basically the same. They use solid state devices, so there's no just the transistors, electronic circuits, and silicon that are storing the information that want. These are non-volatile, and what that means is that if there is no power, if you don't have it powered up, it's still going to store the data. These are non-volatile. These are basically electronic circuits. Compact disk is a disk that spins with lasers that basically reflect off the disk, and then little detectors that come back and read what's coming off the disk, and again decode that into data from the ones and zeros that are modulated onto the CD. So if you've ever seen like an old record player where the record's spinning around and there's a needle and a groove, the CD drive is exactly the same, except the needle's not even grooved. It hovers a little bit above the CD, and it's shooting a laser and detecting the light that comes back up. Our disk drive is almost exactly the same, except it doesn't use light. It's actually a disk that's also spinning. And there it's using a magnetic disk. And the head, instead of a needle that's going to groove or a laser beam that's shooting light, it's a electromagnetic. Basically, it's a magnetic. It's called a read-write head that's sensitive to the magnetism, if you will, on the disk. And it can cause the change in the magnetism on the disk, and that's how you store something. So all these are ways of storing things for a long period of time. Equivalent to all of these things, to the extent that you don't go and scratch it or somehow damage the disk. And even if you do, people government can go back and read the parts you didn't scratch. But to the extent that you don't, it's there. It's there pretty much forever. You can erase a hard disk by magnetism, erase a solid state disk by electromagnetic discharge. Do some things to damage what's there. But otherwise, it's pretty much going to be there. And when you read the data from the disk, it's going to be exactly the data that you put on the disk. The ones and zeros are going to be the same. It may not seem that important. It may seem obvious to you. And when we start talking about the human brain, you see that the human brain doesn't quite work that way. So Another thing that's in common with all these is that they're relatively slow. It takes time to access the information that's here. Now we're going to go over here. When you're running a program, your computer obviously needs to know what to do and has to have access to the data fairly quickly. So when you're going to do that, the instructions and the data that are in the longer term memory, which is kind of slow, are loaded into your volatile memory, which is faster, much faster. And that's the predominant volatile memory that you can load things into is called RAM. And there's lots of different types of RAM. You have RAM in your cell phone. So your cell phone has RAM. Your cell phone has a solid state drive. And if you've got a Samsung or something, then you're going to have the chip that's effectively like a flash chip or drive. And there's lots of different types of volatile memory. Volatile memory is called volatile because once you shut power off to this memory, it bases everything else. And there's different types of volatile memory. SRAM is, as long as you have power to the SRAM, it'll remember, it'll keep in there what you have in there. When you remove power, it'll go away. In the DRAM, you have to do two things. You have to power the DRAM, plus you have to continue to remind it what's supposed to be in there. Because DRAM has very simple cells, where you put a charge in there, over a relatively short period of time, like less than a second, that charge goes away, in which case your memory is lost. So several times a second, the electronics basically have to read the charge that's in there and write back the full amount of the charge that's in there. So if it's 1 or 0, it reads it, okay, it's a 1, and now it writes back the full amount of that charge. Because by the next time it goes to read it, some of that charge that it wrote is going to be gone. If it waits too long, enough of it's going to be gone that effectively lost. Why would you live with something like that? You live with something like that because by having the cell be very small, even though it's not going to hold on to that charge very long, you can put a lot of these cells really close to each other and you can build them very cheaply. So DRAM memory is a lot cheaper than SRAM. So remember, digital computers, we store things for long periods of time very cheaply, but it's a little slow. In order to do something with the instructions and the data, we move it into volatile memory, which is relatively faster than the long-term memory, but also at an expensive cost. And this explains why, like your phone has a certain amount of long-term memory, which is normally bigger than the short-term RAM memory to run the programs and stuff. Any questions on this? It's not the best colors to show up here, but let me make this a little smaller. Okay, the last one is what I call the immediate putting quotes memory. That's not what it's called in the literature. In the literature, it's called a cache. The cache is also used for other types of work. It's supposed to mean like a place that you can access information that you're likely to use. And that's here, and it's close to whatever's going to be processing that information. And basically, the idea is that you have very close to where the processing is happening. You have access to information that your system predicts that you're going to need to compute from. Maybe your system knows pretty well that you're going to need it because your processor is decoding some or compressing some big video file. Right? So it knows what it's going to do next. So basically what happens is the processor looks first to see if what it needs is in its cache. At the same time, it can actually put in a request over here just in case it doesn't find it here. If it is in the cache, then it's done and it just moves on to the next thing. If it's not, then I'll need to wait to get it from wherever it is. Okay, which could be a RAM, could be in short-term memory, it could be in another layer of cache, it could be in short-term memory, or it could be in long-term. Obviously, if the processor needs to keep getting things from long-term memory, it's not running these things. Whatever it is that you're running, it's going to run on the computer very, very slow. So sometimes if you write programs in certain ways, the hardware can come back and bite you because what you think is where you need it isn't necessarily going to be there. This is maybe more of a computer engineering kind of topic, but I think it's important for at least that you know it's there, because sometimes you can do things in the software world that that cause the hardware to really make your life miserable. One thing people do, by the way, is you can create virtual cache. I don't know if you've ever heard of this. Not like virtual money, but you can make this short-term memory a little bit bigger by, instead of keeping it in the cache, using some of your DRAM or some of your hard disk for cache. And it keeps some of your things you're going to need fairly quickly in long-term memory. Now, it keeps it in a place in long-term memory that's going to look for it first, but it's still in long-term memory. So you can get some of the advantages of cache, but it's still not going to be very fast. Okay, and then this is the last slide on digital memory. This is more of what a cache looks like. And these are 3 levels of cache. So if you look at like really high-end processors, like your cell phone or your computer, the microprocessor that's inside of that device is going to have access normally to 3 layers of cache. It's going to have what's called layer 1. So if you have like a 4-core microprocessor, each core is going to have access to 2 layer 1s independently that are dedicated to that core. And a layer 1 cache is just literally the memory that's right butted up to the CPU that it's going to hold before you get everything. To the extent it does, it's just going to be cranking really, really fast. It has the L1s, it has 2 of them, one's for instructions, but it's still what the CPU is supposed to do. And the other one's for data, but it's supposed to do. So the most efficient, highest performing computing you're going to do is when each of your cores is getting the needs from the memories that are adjacent to it. And then the second level of cache is called layer 2. There, it's not dedicated to data or instructions. Both can exist in data or instructions. And it's also not dedicated to any one of the cores. So whereas core 2 can't get any information from the L1 cache that's connected to core 1, both core 1 and core 2 can get information from L2 cache. And then the L3 cache is really sort of an interface cache between the DRAM, which we told you is where your program memory is running, because it's faster than long-term memory, and your other caches. So, because of evolution of computing technology, it's a little bit more complicated than just saying you have long-term memory, like a solid-state drive, and short-term memory, like the DRAM that runs your programs. Because the reality is that most of your programs and your data, when it comes down to it, are actually being fed to the CPU from one of its caches. It's like 3 layers. This is important because as computers get better, faster, higher performance, we're seeing that they need cores that are independent of each other. So they need sort of like mini brains. Right? You can imagine that this core here could be dedicated to video processing. This core here could be dedicated to audio processing. If we have 4 cores or 8 cores or 16 cores, you might have a core for smell processor. You might have a core, or maybe 4 cores that you're going to develop and dedicate to a sense, just to your touch senses, right? To your proprioception. If you want to develop a robot, you might have a computer inside that has 16 cores. And so you want to get maybe information that's coming from sensors from the foot of the robot into the caches that are feeding the core that's processing what it's supposed to do when someone's stepping, when the robot's stepping. This was that problem we talked about earlier, where you don't want the robot inadvertently to step on your head and put its full weight on it. Right? You want it to be very quickly touch the pet, realize something is going on, and not step on it while it's also looking and talking to you at the same time. Right? So how do you implement something like that? In computing, we're actually getting to the point where it makes sense to be able to dedicate a core to every task or subtask that you think is important. And to think about a core, before that when I grew up and when I was working with the computers that were out back in the 90s, and Intel putting processors and things like that. There was no concept of multiple cores, it was just one core. So the computer was a core. And then when the next generation of Intel chips or AMD chips eventually came out, they also had one core. And then the next ones had one core. And then it came to the point where they would add what's called a coprocessor, where they had a very simplistic core that had its own microprocessor dedicated to very specific things. But now when we talk about a core and a cache around it, we're effectively talking about taking what would have been a computer full complete processing power in the 90s and put in 16 of them. 16 better versions of those into your cell phone. We do a lot of that at the same time. Spend a lot of time on this because when you get to the brain, I think that you'll decide for yourself that we must have sort of little cores all throughout our brains. And if we do that, then we need to have memory accessible to those cores all throughout our brain so that they can make decisions and talk to each other. So I want you to start thinking about, a little philosophically, whether your brain is a bunch of neural networks of dumb neurons that either fire or don't fire, or whether your brain is comprised of little neurons that are mini supercomputers that are interconnected to each other and communicating with each other. Because remember, when we talked about the neuron and the log on other cells, we talked about there not just being a billions of them, but that each one has eventually thousands of expressed genes, tons of different dendrites that are connected in different ways. So they're very complex. Complex in such a way that you think that they're doing a lot more than just computing a little bit. Okay. Now we're going to get into the analog world of memory. Let me make this a little smaller so you can read it. The world is analog. And what does that mean, the world is analog? It means it's continuously variable signals. And that's all that analog really means. Whereas in a digital world, you have either some amount of charge or some different amount of charge. That's 1 or 0. Or you have some voltage and different voltage. That's 1 or 0. In the analog world, any one of those cells can have any amount of charge. You can have any amount of charge. Now, if you recall my example as to a DRAM wouldn't be a good way to hold the analog memory, right? Because we said that when you put a certain amount of charge, as soon as you put it in, you start losing something. So if the amount of charge was your analog charge amount, by the time you went in to read it, you wouldn't actually know how much you started. because it would be less. In the digital world, you don't care as long as it's enough that you can say it's a 1 step. So the analog world is a little bit tougher when it comes to saving information because it's continuous. You don't have separation between values. But you still have electrical signals, voltage, current, charge, frequency, and phase. And you have a lot more to work with. So basically, whereas a digital system, you're fairly constrained. Even though you can do a lot with digital computers, we're actually only doing a few different computations. And you have to take everything that you want to do and put it into that digital world so you can do those computations. In the analog world, you can have something that actually does the computation. And you can actually do a lot if you create it specifically for that purpose. I'm going to give you an example of that so that it's not abstract in your mind. So I'm going to talk about the heart. So the heart, I'm not talking about the heart because it has memory. It may or may not have memory. But that's not why I put the heart. There's an application example that uses nerve maps or artificial intelligence networks to analyze behavior of the heart. And it's implemented in an analog computer. And so that's why I'm going to show you how you can take analog memory, analog instructions, and make something useful. Before I can explain, I can show you the data and talk to you about how it works, which I'm going to do. But it'll be a little bit more meaningful if you remember how the human heart works. So I had to remember how the human heart works, so I put this up and share it with you. This is the human heart. And it's basically, I'm just going to talk about 4 parts. Atrium, which is the top little chamber here. There's 2 of them. The right atrium, which I happen to draw on the left to confuse you, and the left atrium, which is actually on the left. And I didn't draw this, I borrowed it from this thing. And then the bottom one is the ventricle, and there's a left ventricle, which is over here. The right ventricle, which is over here. Does anybody know how the heart works? Okay, good. All right, so if I say something wrong, please let me know. Okay, so here's basically how it works. Your heart's about moving blood around. Basically, just bringing blood in, pushing blood on it. That's all it does. If you don't cut yourself, that blood's pretty much just going to mostly stay inside. Right? All right, so in the right atrium, what it does is it brings blood in from your body. It's return blood. It's coming from your veins. That blood is already done in your body with what it was supposed to do. And it's going to bring that into this chamber. Okay, so it's going to fill up the blood. It's called deoxygenated blood. I call it dirty blood. Some people don't like it. It's basically blood that's gone through your whole body. And it's done everything it's supposed to do. And it is true that it comes back without a lot of oxygen in it, because a lot of what it's supposed to do is feed your cells, and your cells need oxygen to survive and do the work. So that blood comes back in here, and it fills up this chamber. I'm going to stop there. So this chamber is filling up of blood that's done its job. On the other side, there's another atrium. On the other side, which is the left of this photo. That blood is actually getting blood also back, but it's blood that's coming from your lungs. Blood that's coming from your lungs, which is why we breathe, has a lot of oxygen. Okay? So this atrium and this atrium kind of do the same thing. They both fill up. One fills up with blood that doesn't have very much oxygen. It's coming from your body. The other one fills up with blood that has a lot of oxygen in it because it just came directly from your lungs. Those 2 atriums at approximately the same time are going to contract. You want to think about contract, just imagine you have a water bottle that's full, and you don't have the top on it, and you're squishing. The water is going to come out because you're supposed to water them. Those are going to open valves to the ventricles. So this ventricle here is all it's going to do is collect basically the blood that was accumulated in the atrium that needs oxygen. And then the other ventricle is going to collect the blood that was collected and transferred to it from the atrium from the lung. So it has a lot of oxygen. So sort of the same thing now. This ventricle is filled with blood that needs oxygen, and this ventricle is filled with blood that has oxygen. So this ventricle and this ventricle are also going to do what the water bottle did, right? Compress and send the blood out. This time, this one that has the blood that needs oxygen, where is it going to send that blood? It's not rhetorical, so please. It's collected the blood from the body of this atrium. Send it over to the ventricle. That's not going to. Where is it going to send that? The lungs, yeah, because it needs oxygen. This ventricle got its blood from this atrium that had just come from the lung, so it has oxygen. When it's compressed, where is it going to send it? To the body. So that's all this happens. So by the time I've been giving you this, all of you have had this many times per day. So thankfully, we don't have to think about it. This process is happening all the time. And this happens, thankfully, without us having to tell our parts about this. The atrium, press. You don't have to do it. It's basically, but there are neurons and there are electrical signals that are going to create pathways that electrically effectively shock each one of these chambers into compressing. So your heart has on the outer surface electrical conduction patterns, and it charges up, and that current, as it flows, causes that muscle about your chamber to compress. If you ever have problems with electrical circuits on your atrium, you will have something called atrial fibrillation. Anybody ever heard of that? It's called AFib for short. It means that your heart will no longer beat at a constant rhythm. Your heart will literally beat and beat, and you'll have to rush to the hospital. Because the electrical circuits basically will be short circuited. Your heart will still be compressing that atrium, but it'll be doing it sort of randomly, which means that your ventricle is going to get some variability in supply, and it's not going to be pumping out what it needs to the lungs. Right? And if your atrium's messed up, either one of them, then the other one's not going to be pumping it, so it goes into your body. As a side note, I can tell you this is a very real problem because this happened to me. I was sleeping in Dallas, Texas, a number of years ago, and I woke up because my jaw hurt. I was rolling around in bed trying to figure out a comfortable position for my jaw. When my jaw just hurt. So I did a Google search, woke up at night, jaw hurt. Thankfully, what came back was you could be having a heart problem. Okay, so I got dressed, I got in my car, drove to the hospital in Dallas, stopped, got some gas on the road, got to the hospital, got to the emergency room, walked inside, the lady looked at me, she said, come on back. And my heart was literally beating at approximately 100 times per second. Because it was just beating randomly and the heart wasn't getting enough oxygen, which caused it to be even faster to try to compensate, but it was never going to work. I don't have this problem anymore because I had something that's called an ablation, which means they literally go to the surface of your heart and burn little sections of it so the current just doesn't flow everywhere, it only flows where it's supposed to. 100% fixed. But that's aside. Okay, so now that we know how the heart works and why it's important that it works well, we're going to get to an application. So there's something called an ECG, which is nothing but a fancy word for saying that with electrodes here, because the heart, as I just told you, is an electrical system, and it's that electricity that causes it to do what it's supposed to do. You better do it in some timing, right? So nutrients are doing something, vegetables ready, it takes the time it's supposed to, it gets it out, right? Because the nutrients fill it out. The vegetable just decides it wants to all break. The nutrients not going to be able to pump what it's supposed to do, right? It's going forward. So everything's supposed to work better than clockwork. And if you put electrodes here, you can actually monitor the electrical signals that are causing this to happen. And you get a curve that looks something like this. And that curve has different regions, and they have different names. This region is called P, which is the atrial systole contraction pulse, which is a fancy word for saying this is the electrical signal that you're going to get on probes that you put on someone's body when the atrium does this. That's the atrium electrical signal causing it to do that. All right. Then we're going to get to this R point, which is the peak of the ventricular contraction. I'm not going to ask you because I know you already know what this means. This is when the ventricle, not surprising, much bigger signal, the ventricle is a bigger beast, if you will, it's going to contract. Right? Send the blood into the lungs or to the body. And this T is what's called the recovery of the ventricle. So there's some electrical signal that's sort of getting that water bottle back into the shape that it's supposed to get to, so we can go through this over and over and over. That's how many times this is happening. Okay. So let's imagine we have a plotter. I don't know if you know what a plotter is, but a plotter is you take these electrodes, you have this analog signal, remember we're in an analog world now. You connect that analog signal to a pen, and there's a moving piece of paper, and this pen literally is moving up and down depending on the magnitude of that analog signal. There's no digital anywhere in this, it's just moving it up and down. The more the signal is, the more it moves it up. And then everything in the world's good, the paper's moving at a constant speed. And then that pen is literally plotting this. So you look at this, and you're supposed to decide, like, is this guy okay or not? Or you can build an analog computer to decide. And what do we mean by an analog computer? Really, we just mean that you're taking analog signals in, electrical signals, reacting, voltage, charge, frequency. And you're doing something to that, and you're outputting analog signals. So there's no digital anywhere in this. Inputting analog, outputting analog. You create circuits in that analog that create the mathematical functions or the algorithm that you want to perform. If you want to integrate, then we create circuits that have capacitors because capacitors integrate. So you change your electrical signal in a way that's related to the algorithm, and you implement the algorithm based on analog circuits. This is just an example. You don't need to know the details of this. But this is an example of what's called a nonlinear filter. And so back in 1966, 67, there was a paper where they built an analog computer to do just this. And the reason they did it is because it turned out that if a physician, a doctor, a well-trained doctor, medical doctor, looked at these plots, if it was normal, they would guess that it was normal 95% of the time. So if it was normal, they would say it's normal 95% of the time. But if they were presented with one that was abnormal, where that person had some issue, they would only get it right 53% of the time. You would say that's horrible, right? So someone's got something going on, they look at it half the time and say, hey, you know what, it looks okay. It doesn't necessarily mean that half the people are going off and dying because the doctor missed it. Okay? What it means is if it was just that, if they were just looking at it, they could also be looking at the patient saying, hey, I have chest pain. Right? And then they look at the ECG and they say, well, the ECG, and maybe they missed the ECG looks okay, but they have chest pain. So we're still going to use some other thing. But this was just, if all they could see was the ECG. So you take someone else's patient, and put it in a bunch of doctors and say which ones are good, which ones are good. They built this analog computer, and the analog computer was able to take those same ECG signals, and 97% of the time for that data set, accurately predict when it was normal, and 90% of the time predict when it was abnormal. That's just looking at the ECG. So what this suggests is that the ECG data actually had the information, but just looking at it in a plot wasn't enough for the physician to be able to see it. So what they built, and it's described in this paper by SPECT, is basically a pattern recognition based on polynomial discriminants or nonlinear filters. And I just thought this was curious because the conference, he presented this at IEEE conference on pattern recognition that happened to be held in Puerto Rico in 1966. It was pretty random. Long time ago, but actually that's even before I was born. Okay, so what does this thing actually have to look like? So this is basically what they built in that analog computer. What this is the frequency transform or frequency response of an ECG signal. So you take an ECG signal, pretty what I just showed you, you take a bunch of them, here they took 150 of them, and you run it through an FFT or some Fourier transform to figure out what the frequency components are for that signal. And you get a plot that looks like this. Here they're just showing the contributions within the ECG signal of different artifacts, like versus mood, and it might look like that. So what you do is you take an ideal ECG signal, like this one, and you build a filter. So you build that electronically as a filter using analog signals. What does that mean? That means if you have an ECG signal coming into this filter, its frequency composition and distribution is going to be equal to the filter you just built. So that's why they call it a matching filter. It's going to match what you put in. Because it's going to be equal, it's going to come out effectively the same. It's going to come out the other side. It's not equal, then you're going to get attenuation because it's not equal. It's not equal, and you have higher frequency components, they're not going to make it through. If most of your intensity is not where it's supposed to be, it's going to be attenuated. You have very low intensity over here where it's least attenuated, it's going to come out small. So not very much is going to come out unless your input matches what your filter is. But this filter is fixed. You can vary potentiometers to change resistance and things like that. But it's a filter. So when the signal comes in, instead of sending it to your fodder, you send some of it to your fodder, send some of it to this filter, which is an analog filter. You're going to get something on the outside that's going to tell you how well it matches to what it should look like. It's a very simplistic computer, if you will. You bring in your analog signals, they go through your analog matched filter, and if a lot of signal comes out the other side, then that ECG is normal. That person's okay. At least 97% of the time accurate, and 10% of the time inaccurate if it's abnormal. If it's low, then it's abnormal. We have a few minutes here, and so I know there's a lot to cover. Okay. And I say a lot of times in class that this is important. This is important Why is this important? Because to take artificial intelligence, human perspective artificial intelligence, to another level, which is to replicate it's actually more consistent with what's happening in the brain. I think you're going to come to the conclusion as we go through this class, if you haven't already, that we're not going to get there through making computers that we have today, the way they work today, bigger, faster, more of the same thing. We're going to have to include different types of processing, different types of ways in order to give. Maybe the central part is really do some processing ways to give a better chance of making decisions like not stepping all the way down. And so that's why it's important to understand that there's another world out there on how to process information. It's an analog world. And our bodies use this a lot. We have time for just a couple of questions. I feel like there has to be a question. It's not that clear.
So you're saying this is that there can be a mix between the analog and sending those signals would be other types of things, and with that you need better capacity in AI.
Absolutely. And when you read those articles, which are relatively short, what you're going to see is you can actually even train an analog. So you can implement a neural network, which they used to call nerve nets, in an analog computer. So you can actually change the weights, and it can train and learn, and it's get a labeled sequence of images. Okay, I have one more slide for today. And then I'll leave you with one slide just about next time. This is an analog computer from 1945 that was developed by a company called Norden. To my knowledge, Norden doesn't exist anymore. What this computer does, and it's done in the same kind of manner. Here, we're looking at making a decision. Is this ECG heart good, or does this person have some problem? Right? So we built a filter. We matched it to what a good signal should be. So we can look at the output and decide is it good or is it not. Here, this is a little bit more complicated computer. This computer is doing is it's taking the wind speed and direction of an airplane flying at a given altitude, and it was computing the timing for dropping the problem. That's basically what it had to do. So it knew where the target was, and it knew where it was. And in a world where the plane's not moving slightly in this direction, where there's not wind and the velocity's not changing, you could just on a piece of paper basically calculate where that was supposed to happen. In a world where you do have these variables, they needed a computer to do that. And this is the computer that was secret for a long time, but now it's typically available. Basically what it does is that. So it's optical and mechanical. It's not digital in any way. It's an analog computer. It's meant to determine when to drop a bomb based on where you want the bomb to hit and how fast and what direction it's going. So that's the most complicated computer in terms of inputs and outputs, but a fairly sophisticated task to try to compute back in 1945, which was a long time ago, 75 years ago. This is where we're going to start next time, which is on the human memory. We're probably going to spend, I think, 2 classes on it. See how far we get through next class. But when we get here next class, I want you to come awake, because the first thing we're going to do that class is we're going to get together in a circle, basically, and start mapping out together how the human memory Because I think that with your inputs, we're going to put together a pipeline. You haven't done it, so what's going to happen? I think with your inputs, your attention, your commitment, we're going to pretty much put together a good part of what's commonly known about how the human mind works, just by analyzing how each of our own members work. Okay. Thanks.